Hi everyone, I'm going to be talking through my experiment for Lab 1. Introduction. The purpose of this lab is to create a model to show constant velocity in both the experimental sense and a theoretical prediction. Newton's second law of motion is demonstrated in this lab experiment. This law states an object's acceleration is dependent on two variables, the mass of the object and the net force on the object. Since, in my experiment, there is no net force on the ball after it leaves the contact of my hand, the acceleration of the ball is zero. This means that the velocity of the ball is constant. The results of this lab show the experimental and predicted values to be very close, meaning the experiment closely resembled an ideal environment with negligent friction and drag. So this video is what I used for my experiment in Tracker. Models. As stated previously, the purpose of this lab is to model an object moving with constant velocity and without changing direction. In the experimental model, we can see the ball remains in motion in the same direction from beginning to end, and there is no force added to the ball while in motion, so the net force can be assumed to be zero. Experiment. The initial conditions include the initial position, which was 0.003 meters, and the initial velocity, which was 1.822 meters per second, which was approximated from Tracker. The system was the ball, and the surroundings included the Earth. Using Tracker, we can determine an approximate velocity at each time interval. The experimental velocity is not entirely constant, but this can be explained through friction between the ball and the floor, which cannot be removed. So if you can see in this picture, the velocity is shown in green here, so it is not constant and it is sloping downwards slightly. However, both of those can be determined or explained through Tracker using errors and also friction. Code. The code for this lab is made to model Newton's second law. The velocity variable is shown as the velocity plus the net force divided by the mass times delta t. This models kinematic motion in physics. However, in this case, since the net force is zero, the second term becomes zero, therefore showing that the velocity is constant from start to end. So if we can see in lines 36 and 37, the vectors that initialized the position and the velocity of the ball were taken from the initial conditions from Tracker. So this was the 0.003 meters, that was where the position started. And the initial velocity was 1.82 meters per second. And then the final, or the t, is the final time that it took in Tracker. Discussion. In this chart, we can see the predicted and observed positions plotted against time. The graph shows the observed position to be nearly identical to the prediction until the last 0.5 seconds. This can be explained due to friction and other external forces acting on the ball, since it is not an ideal frictionless surface. Error could have also occurred in using Tracker, where the frame rate might have been different, or I did not click the point mass in the same spot on the ball in every frame. Now the what if question. What if? So I chose to set the axes in this experiment so that the ball would travel in the positive x direction, which also showed the velocity as positive. However, if I had set it so that the ball was traveling in the negative x direction, it also would have reflected on the velocity to be negative. Now, what does this mean? In the y direction, the two forces acting on the ball cancel out to become zero, the force of gravity and the normal force. However, in the x direction, it is unclear exactly how many forces are acting on the ball, such as drag, friction, or an inconsistent push to get the ball moving at the beginning. So we are unable to determine exactly the number of forces that were added together in the x direction to make the net force zero. In conclusion, this experiment very closely modeled constant velocity of a ball. I demonstrated Newton's second law, which says acceleration is dependent on mass and net force. In this scenario, the acceleration was zero due to the net force being zero, which also meant the velocity was constant. The computational model I developed using the experimental data also showed this at an ideal case where the system is isolated and has no external forces like friction acting on the object.